Hello everybody, welcome. This is May 2023, paper 2, and it's from time zone 1. Okay. Question 2, 16 mark question. Here we've got a function. Consider the function f of x is equal to 3x minus 1 plus 4x to the negative 2. So raised to the power of negative 2 right here. Part of the graph of y equals f of x is shown below. Here's our graph. The function is defined for all values of x, except for some value when x is equal to a. Write down the value of a. That's our first question. So we've got this original function here. It's f of x is equal to 3x minus 1 plus, and this 4x to the negative 2. If we have x to the negative 2, what we actually have is 1 over x squared. Just like when we're doing calculus, for example, and they give us a function like 3 over x, we would write this out as 3 to the x to the negative 1, 3 times x to the negative 1. In the same way that we have this 4 times x to the negative 2, or to the power of negative 2, what we actually have here is a fraction. And so we can write this last part as 4 over x squared, essentially. And that will be useful for us here. We can also solve this graphically, writing down the value of a. So it says our function is defined for all values of x. That is to say, we can put in any value of x that we want into here, except for one single value. And since our function is f of x is equal to 3x minus 1 plus 4 over x squared, there's some value that we can't actually put in. And that's when x is equal to 0, because then at that point we have 4 divided by 0, which is illegitimate. It's not something that we can actually solve for. Another way to possibly look at this is just graphically. You can ask, where is our vertical asymptote? So we approach infinity here as we move from the left to right, and then again as the right to left, and it approaches some value. And just by inspection, this isn't necessarily like the rigorous way to solve it, but if we're looking at this, when the value is x is equal to 0, it looks like at this point we're reaching infinity, and we're not actually going to have a value at this point. It's going to approach some value, it's going to approach positive infinity, but we're not actually going to reach some value. So write down the value of a, just one mark question, when a is equal to 0. More algebraic answer is, well, because when a is equal to 0, or when, let's say, x is equal to 0, we're suddenly dividing by 0, which we can't do. But just graphically, you can see that there's this value that we approach and don't reach. Alright. Part B. Use your graphic display calculator to find the coordinates of the local minimum. 2-mark question. Not bad. Let's go to the calculator and work this out. Let me get a new document. Alright, let's go into the graph calculator and graph this function. So 3x minus 1 plus 4x, and the calculator will accept this. We don't need to write this as 4 over x squared. We can write 4 times x to the negative 2. Alright, so there's our function. Don't need to do any kind of zoom fit. And let's find the local minimum. So let's analyze graph. Let's find the minimum and see where it occurs. So when x is equal to 1.39, the y value is 5.24. Alright, let's go back to the document and write that out. So they're asking for the coordinates, so let's put both the x, y values. That would be when x is equal to 1.39, y is equal to 5.24. Okay. Next part. The equation f of x is equal to w, where w is some real number. So you can read this as, it actually is an element of the real numbers, but is, and then some real number. And a real number is anything that you could put on a number line. So 0, it could be 1, 2, 3, 4, it could be root 2, it could be anything that you could put on a number line, from negative to positive infinity. So we're looking for some equation where our function is equal to w, and we have 3 solutions. So this is kind of maybe a question that tests terminology or understanding of terminology in functions. Really, when we're talking about a solution of our function with some value, we're talking about graphically intersection points. So if this is our function right here, f of x is equal to 3x minus 1 plus 4x to the negative 2. What we're asking is, what's this value of f of x? What is this value w? What is it in this case? What is it in this case where we'll have 3 values of x, where we'll have 3 solutions? So 3 values of x. And in this case, graphically, if we look at our original function, in this case, let's draw one line, for example. This would be y is equal to 3, or in this case, w is equal to 3, and there's only one solution, there's only one intersection. Often IB questions lead into each other. They just asked us to find the coordinate of this minimum point, for example, right here. And if we look and we were to graph, let's say, any other line for w in this case, if we suddenly graph, let's say, y is equal to 7, now we have 1, 2, 3 solutions, or 3 x values. We have x1, this is x2, x3. We have 3 x values which will provide a solution, which will produce an output of 7 in this case. And really, if we want to answer this question, identify one possible value of w, it's anything above this point, this y value of 5.24, that's the minimum, anything above that. So we could say that w is equal to 7 or something like that. Really anything above 5.24. Okay. Part D asks us to write down whether the value, the line y equals mx minus 1 over 4 is tangent to f of x when x is equal to negative 4. Write down whether the value of m is positive or negative. Justify your answer. So the line y is equal to mx minus 1 over 4 is tangent to f of x when x is equal to negative 4. Write down whether the value of m is positive or negative. Justify your answer. Okay. So we've got this function right here. It looks like this, and then it kind of goes down like this. And what they're saying is there's some point when x is equal to negative 4. So when x is equal to negative 4 at this point, negative 4, actually let's change that just to make it map on a little more. When x is equal to negative 4, the question is, what is the slope? And we have negative 4 here, and who knows what y value it is? We can find that. What is m? What is the slope of this tangent line? Okay. Is it positive or negative? Justify your answer. And in this case, it doesn't seem, I actually looked at the mark scheme earlier, and a graphical solution of just graphing it and seeing whether it slopes upwards or downwards won't actually be a mark in this case. We want us to do some kind of algebraic work. So this is the slope of the tangent line. Y is equal to mx minus 1 over 4. They tell us it's tangent to our function when x is equal to negative 4. Write down whether the value of m is positive or negative. One thing we can do is we can look at our original function and we can find the derivative, that is to say the slope function, and we can input this negative 4 and ask, okay, well, what is the slope at this given point? So our original function itself was f of x is equal to 3x minus 1 plus 4x to the negative 2. And it's nice because they already gave us this to the negative 2. And one way we can do this is we can just find the derivative. And 3x to the negative 1, or sorry, 3x to the 1 just becomes 3. Constants just disappear. And then dealing with this value right here, we'll multiply by negative 2. So this would give us negative 8x, and this was negative 2, and now it should be negative 3. This isn't a heavy calculus question, so I'm not going to go over the derivative rule. It's in your formula booklet. Actually, I guess I'll write it down here. F of x is equal to x to the n. F prime of x, that is to say the derivative, is we're multiplying by the exponent, and the exponent decreases by 1. If we have just x, it disappears, constants just become 0, and then we can follow that rule for this last term right here. And so that is our derivative function. Our derivative function is also something that allows us to find the slope at a given point. It's also called our gradient function. So we can find the value of -4 at this point. We're asking the question, okay, well, what is the slope when x is equal to -4? And we can put this into the calculator. Actually, that's what I'll do here. So we have 3 minus 8, and then we have -4, and we raise it to the power of -3. We find out that it's positive. So going back to the document for a sec, we know that f prime of -4 is equal to 25 over 8, and that means this is our slope. This 25 over 8 is our slope when x is equal to -4. So right here we know that m is equal to 25 over 8 at this point. And so it is positive. That's one way to work it out. Another way, which doesn't require calculus, is just looking at this line itself. This y is equal to mx minus 1 over 4. And they give us an x value of -4. So we could put that in. And if we know an x and y value, then we know 2 out of the 3 unknowns, and we can solve for m. So let's go ahead to the calculator screen once again. And this is our function. And let's ask the question, going to graph trace, what is the value when x is equal to -4? And so, I mean, like we can see right here that it's positive. The slope is positive. It's going up. But working it out algebraically, when x is equal to -4, y is equal to -12.8. So we can substitute those values into our equation, and we actually just have m left as an unknown, and then that would give us a value of m. So going back to the document, let's write this out. We have y is equal to mx minus 1 over 4, and on the calculator we found out that y was equal to -12.8 when x was equal to -4. And now we have an equation where we just have some equation in terms of just one variable, just in terms of m. And we can go ahead and end solve this. That's actually what I'll do here. So back at the calculator screen, menu, algebra, numerical solve, and we'll go -12.8 equals m times -4 minus 1 over 4. I'm just going to put that as 0.25 and ask the calculator to solve for m. Oops. Their function is not defined. Okay. So something went wrong. Y is equal to -12.8 when x is equal to -4. Okay. Y is equal to -12.8 when m is equal to -4. Function is not defined. So what they're saying is that there's going to be no value there. But I don't believe that's true. So it's possible that it's not liking this. Let's see if that helps. Okay. That's interesting. 3.1375, which as a fraction gives us 25 over 8. So once again, the important thing is just that this value of m is positive. So m we found is positive. Write down whether the value of m is positive or negative. M is positive. So going back to the document here, m is equal to 3.1375, and we know that it is positive. Okay. So kind of a tricky question. There's a lot of, I guess, terminology. This one requires some understanding of asymptotes, I guess. So lines that we approach but never reach. This one requires an understanding of what are solutions, so intersections between two functions. This is an interesting question that would require either some calculus to find the gradient function or the slope of a line at a given point, or just knowing that, okay, we have an x and a y value, how can we solve for m, this missing value? If we have 2 out of the 3 unknowns, can we find it? It's interesting that they wouldn't accept a graphical solution, even though it's clearly positive, right at -4, for example. Alright, let's continue on. A second function is given by g of x. So remember, we can call our functions different things. Often we say f of x, but we can call them g of x, h of x, q of x, p of x. It's just a different name for a function. It's like y1, y2, y3. So a second function is given by g of x is equal to kp to the power of x minus 9, where p is greater than 0. The graph of y is equal to g of x intersects the x-axis at points a, which is 0, -5, and it passes through the points b, 3, 4, 5. So a lot going on here. It's pretty dense. What do we have? We have some function, and it's given by k times p to the power of x minus 9. And x is just our variable. Like, we can see g of x is equal to y, and that's exactly what they do here. So it's more or less like y is equal to k times p of x minus 9. And there are these things that we don't know. We don't know p, and we don't know k. But it's some kind of exponential function. And exponential functions, remember, are ones that look often like this, and they go off into infinity, or they start low and then they kind of decay and so on. That's what this is. An exponential function is when our variable x is in this is power, is as an exponent essentially. Okay, so that's what we've got in this case. We've got some function. It's an exponential function. It's going to go off into infinity, or it's going to decay. And the question is, the first part of it is find the value of x and then find the value of p. Okay, so this one's kind of tricky. If we're looking at this function right here, y is equal to k times p of x minus 9, we have 1, 2, 3, 4 unknowns. And how can we solve for k? K is this value right here. It's kind of a tricky question, but they give us these 2 points, 0, -5, and 3, 4.5. This value right here, this 0, is going to be significant because it's a point when x is equal to 0 and y is equal to -5. And just like our linear equations, for example, when we have y is equal to mx plus b, if x itself is equal to 0, it also, in this case, it would take away our m value, and it would give us our y-intercept right away. And something special also happens when we're dealing with exponential functions. When x is equal to 0, we have p to the power of 0, and we know that anything to the power of 0 just becomes 1. So we have some function. We don't know these two values, this value of k, this value of p, but they did give us 2 points. What makes this kind of tricky, or at least so far as I see, as far as I think, it's not a straightforward input-output question. We have to decide. And you can kind of use process of elimination. If we have some unknowns and we have some given points, it's often the case that we're going to want to substitute some of these values. And in some sense we could try this and then nothing would really happen. But when we try this value, we can get a result. So let's go ahead and substitute this value of a right here. Okay. So for a, we know that this is our x value and this is our y value. So let's substitute those values in. So for k, we have -5 is equal to k times p raised to the power of 0, and it's minus 9. And we said earlier that p to the power of 0 was just 1. So now we have negative 5 is equal to k minus 9. And we can end solve this if you want, or just a little algebra, and we have k is equal to 4. Alright, so that's the first value of k. So, knowing that piece of information, let's actually put that into our function right here. So we have y is equal to, we know what k is now, we don't know what p is, px minus 9. Now we have some function with 1, 2, 3 unknowns, and we've got another point that we've never used. So in order to find this value of p, we can plug in a value of x and a value of y, and then that should allow us to find this unknown right here. So let's go ahead and work that out for part 2. Might need that space later, so let's just substitute. So here we have another xy value, or xy coordinate point. Let's substitute 4.5 equals 4. P we don't know. X is equal to 3 minus 9. And this one actually going to go ahead and, I don't know why that doesn't work. There we go. Gonna go ahead and solve for p in this case. So let's go back to the calculator and work this out. Menu, algebra, numerical solve. 4.5 is equal to 4 times, let's say p to the 3 minus 9, and then ask the calculator to solve for p. Okay, in this case p is equal to 1.5. So let's go back to the document. P is equal to 1.5. So kind of a tricky question, but potentially through elimination. Like when you're given an equation such as this and you're asked to solve for an unknown, most often, not always, but most often, especially when they give you points, they're asking you to substitute into the equation to solve for the unknowns. What makes this one a little trickier is they give you 2 options and order actually matters. So in this case, we need to substitute this 0, negative 5. 0 you can kind of remember as a special value, and it often helps clean things up. Or in this case, eliminate a variable that we don't exactly want. And so, in this case, order matters. Substitute this, and then afterwards we can substitute the second value to find p. Alright, question F right here. Write down the equation of the horizontal asymptote of y equals g of x. So what are they talking about when they're talking about a horizontal asymptote? Horizontal asymptote is a line that we approach but never reach. So we looked earlier, we had that vertical asymptote all the way back here. This is our vertical asymptote, this line that we approach vertically but never reach. And that was at x is equal to 0, that vertical asymptote. A horizontal asymptote is a line that we approach and never reach. So if we have, let's say, typical example is a cooling cup of tea, and we have some exponential function, and then eventually this function is going to approach, or this teacup in this case, is going to approach but never really reach. I should do that a little lower, I suppose, but never going to reach this certain temperature, in this case like room temperature, for example. Another example would be if someone is jumping out of an airplane, parachuting, they would have, some 0 point of their initial speed, and then after a while they would reach what's called terminal velocity, and then again there would be some point that they would approach but never reach. This is what's called a horizontal asymptote. In this case, what is the horizontal asymptote of this function y is equal to g of x? What is the line that we approach and never reach? So here's our function. y is equal to 4 times p of x minus 9. Or sorry, not p of x, we know p. So 4 times 1.5 multiplied by, or sorry, raised to the power of x minus 9. Remember, order of operations, don't be tempted to multiply 4 and 1.5 together and just write it as 6 to the x. That would not be correct. Order of operations, it's 1.5 raised to the power of x, then multiplied by 4, and then you take away 9. So don't simplify anything, just leave it as it is. That's our function. Okay, horizontal asymptote. Generally, I mean, we can graph it to find out, but what can we say? What can we say? I don't want to go and give too lengthy of an explanation, but if we have this function right here, and we have certain x and y values, so here's x, here's y. When x is equal to 0, remember this goes away and we'll have, sorry, this right here. When x is equal to 0, this 1.5 will just become 1, and we'll have 4 minus 9, and this itself will equal negative 5. So that's a point we already had, 0, negative 5. And then we can ask, okay, well, when x gets bigger, when x becomes 2 or 3 or 10, we have 1.5, for example, raised to the power of 10, 1.5 multiplied by the power of 10. It's just getting bigger and bigger and bigger as x becomes larger. So 1.5 raised to the power of 10, 1.5 multiplied by itself 10 times, times 4, and so, and then we just take away 9, which becomes less and less significant. So it gets bigger and bigger and bigger. In this case, our function will look something like this. So it starts low and then it goes off into infinity. And then when x is less, when we go the other way in this case, well, what happens is x itself will become negative. And without going into too much detail, 1.5 to the negative x is just 1 over 1.5 to the x. So we're dividing 1 by some massive, massive number to the point where when we multiply that super, super small number by 4, the 4 kind of goes away and we're just left with this remainder, this negative 9. So it becomes very, very small. When we go this way, this becomes very, very large. But when it becomes very, very small, there's some value that doesn't go away, that's always by itself. This negative 9, it's not affected by what happens here with this x. It's just by itself, this negative 9. And so what does that mean? When x becomes very, very small, we reach some asymptote, some line that we approach but never reach. And in this case, it would be y is equal to negative 9. So write down the equation. The equation means we're asked for an equal sign. The equation of the horizontal asymptote. In this case, it's going to be this horizontal line. Remember, our horizontal lines are always in terms of y, right? So this would be like y is equal to 4. Above here, we had this value of y is equal to 7. These are our horizontal lines, right? And our vertical lines are, in this case, x is equal to 0 or x is equal to 2. These are our vertical lines, and these are our horizontal lines. So if we want to write an equation, what is our horizontal asymptote? It's negative 9 in this case. I want to show you really quick how to potentially do this on a graphing calculator. So going back to the graphing calculator for a sec, let's put in our function 4 times 1.5 raised to the power of x minus 9. And so we've got this function, and if we, let's say, zoom out and just keep zooming out, I mean, right away we kind of already see, okay, what's this line that it's kind of settling on, this horizontal line. It seems to get flat. It doesn't go much beyond this point. In this case, we can just use graph trace. Graph trace will give us some kind of point, and we can just keep going to the left and left, or we could put in some massive value in some cases. But already here it looks like we're settled on this value of negative 9, and this is the value that we rest at in some sense. It never goes lower than this point. This y is equal to negative 9. And so, once again, you can solve it this way. What's our horizontal asymptote? Y is equal to -9. Alright, part G. Find the solution of f of x equals g of x when x is equal to 0. So this, again, I mean, try not to be... I mean, the notation could potentially be intimidating. This f of x is equal to g of x. So what does this f of x equal to g of x mean? It means we have this one function and this other function in less kind of like maybe more intimidating function notation. It's like we've got an equation of y1 and y2. So when does y1 equal y2? So this is our g of x right here, and f of x was on the previous page. So what they're asking is, okay, well, we know one of the functions looks kind of like this, and they have this other function up here. When do they meet? When does the first function, f of x, equal the second function, g of x? When are they both equivalent? When do they both have the same value? And there's two ways we can solve this. We can either n-solve or work this out graphically. So let's n-solve this potentially first, and then we'll work it out graphically. So f of x, I've got to go find it right here. 3x minus 1 plus 4x to the negative 2. Alright. 3x plus 1 minus 4... 4x to the negative 2. Minus 4x to the negative 2. And this other function was, I believe, 4 times 1.5 to the power of x minus 9. There it is, okay. And to be honest, if we just want to find out when does f of x equal g of x, we can just n-solve this equation and solve for x. Sometimes n-solve actually has some trouble with exponentials, but in this case, it's possible that it will work. We may need to graph it, but let's see if we can n-solve this first off. Okay. Menu, algebra, numerical solve. 3x plus 1 minus 4x to the negative 2 equals 4, and then I think it didn't really like that. 1.5 to the power of x minus 9, and we want to ask the calculator to solve for x. So it looks rather intimidating, but essentially we're saying, when does this one function, which we defined as this kind of rational equation, this rational function, when does this one function equal this other one? And it actually worked in this case. Okay. X. So we'll go back to the document and write this out. So the value that we have is equal to 0.7647. So we'll write 74671 and so on to 3 sig figs 765. Okay. Not bad. Graphically, I hope this isn't too long-winded, but I'll give a quick demonstration of what's happening graphically. This is one of our functions. This is g of x, right? This exponential function, which is going off into infinity. This is g of x. And then we had f of x, that original function. Remember, it went down like this, and then it had its minimum, and then it went across. And there was that point where, what did it look like? It looked something like this, actually, yeah. And then it had that vertical asymptote right here, and then it went off. Okay, so actually looking at this graphically, it looks like there might be two solutions, which might be something that n-solve might miss. Ah, I see. I'm sorry, this is my mistake in reading this. Find the solution of f of x when x is greater than 0. So although we might have two solutions, it's when x is greater than 0. So we're really just looking for this value right here. So let's go ahead and graph it, and we can look at this way to do it as well if you're more comfortable. Feel free to skip ahead if you're happy with the n-solve method. Okay, so here is the original function that we had. Actually, That's all right. 3x minus 1 plus 4x to the negative 2. That's our original function. Let's go menu, graph entry, function, and let's put the second function in, which was 4 times 1.5 raised to the power of x minus 9. Okay, looks like we have our intersection right here, and this should give us the equation. So analyze graph, intersection, and in this case, it gives us a different value. 3x plus 1 minus 4x to the negative 2. 3x, I wrote 3x plus 1 on that original NSolve question, but it's actually 3x minus 1. So here we go. Let's write this out. I'm going to go back to the document and write this out tentatively as x is equal to 4. And I'm going to go ahead and type this quickly back into NSolve. Okay. Menu, algebra, numerical solve. And so we have 3x minus 1 minus 4x to the negative 2. And this should equal 4 times 1.5 raised to the power of x minus 9. Then we want to solve for x. We actually just make sure that these are all correct. 3x minus 1 plus 4x. Okay, so maybe there's something to be said about an NSolve method. It's 4x to the negative 2, and then going down further, 4 times 1.5 to the x minus 9. This looks good, and hopefully it gives a value of 4. Otherwise, I'm not sure. Ah, geez. Okay, that's not terrible, actually. It's finding the closest value. So what NSolve is doing is it's finding the closest value to 0, and we know a value of 4 is actually further away. So taking this again, and then asking NSolve to solve for something, let's say, beyond 2, for example. What could we do? In this case, we want to solve for something greater than 2. I'm almost wondering whether NSolve is going to be an appropriate strategy. There is a way to ask NSolve to solve after a given point, but I'm not exactly remembering it here. I'm looking for this function where it says greater than. Not sure if we can say x is greater than 2. Let's see. X is greater than 2? No. Okay. X. Did we put comma 2 in here? There it is. Okay. So there we go. If you want NSolve to solve after a given value, normally NSolve will solve the closest value to 0. If we want NSolve to solve after a given point, or closest to, in this case, closest to some value, in this case we can put in larger and larger values. I believe what this case is, it asks you to solve something greater than 2. In this case it gave us that value of 4. Okay, not a bad learning experience. I apologize if it was a little drawn out. I guess maybe it shows that NSolve can have its risks, I guess. Alright everybody, I hope that was helpful, and as always, best of luck. Take care.